Hello everyone. Let me start with a thought. Why does it feel harder to swing a cricket bat compared to a simple stick of the same weight? The reason is not just mass, but how that mass is distributed. In linear motion, we use mass to measure inertia, the resistance to acceleration. But in rotation, the resistance depends on both the amount of mass and how far it lies from the axis of rotation. Take a particle of mass m at distance r from the axis. Its kinetic energy is half m times r squared omega squared. Summing over all particles, we get half omega squared times summation of mr squared. This introduces a new parameter, the moment of inertia. It's the rotational analogue of mass. Formally, for n particles at distances r sub I, the moment of inertia, I, equals the summation of m sub I times r sub I squared. That's equation 6.34. Now, the rotational kinetic energy of the body can be neatly written as 1/2 I omega squared, equation 6.35. Notice how similar it looks to translational kinetic energy, 1/2 mv squared. The unit of I is kilogram meter squared and its dimension is ml squared. Importantly, I does not depend on angular velocity, it depends only on the distribution of mass and the geometry of the body. Let's check simple cases. For a thin ring of radius r and mass m, all mass is at distance r. So I equals mr squared. For a light rod of length L with two equal masses m over 2 at its ends, the calculation gives I equals 1/4 ml squared. These examples show how moment of inertia depends strongly on the distance of mass from the axis. In fact, doubling the distance quadruples the contribution.
To simplify things, physicists use the concept of radius of gyration. Define k such that I equals mk squared. It's as if the whole mass were concentrated at a distance k from the axis. For a thin rod about its midpoint, k equals L divided by root 12. For a disk about its diameter, k equals r over 2. This concept makes comparing bodies much easier. Different mass distributions can be reduced to an equivalent single distance from the axis. Over time, standard moments of inertia have been calculated for common shapes. For a thin ring, about an axis perpendicular to its plane, I equals mr squared. For a thin rod about an axis through its midpoint, I equals ml squared over 12. For a solid cylinder about its axis, I equals mr squared over 2. And for a solid sphere about its diameter, I equals 2/5 mr squared. All these values are neatly tabulated in table 6.1 of your textbook, and they are essential for solving real problems quickly. So what does I really tell us? Just like mass resists linear acceleration, moment of inertia resists angular acceleration. If I is large, more torque is needed to achieve the same angular acceleration. That's why heavy flywheels are used in engines. Their large moment of inertia makes them resist sudden speed changes, keeping the system stable. So while mass measures translational inertia, moment of inertia measures rotational inertia.
Let's take a real-life example, the flywheel. It's a heavy rotating disc used in engines to smooth out speed fluctuations. Step 1. Its kinetic energy is half I omega squared. Step 2. Because I is large, the flywheel stores a lot of energy at the same angular velocity. Step 3. If engine torque fluctuates, the flywheel releases or absorbs energy gradually. Step 4. The result is steady, smooth rotation, preventing jerks in the machine. That's why even though flywheels add extra mass, they are indispensable in automobiles and steam engines. So to sum up, the moment of inertia is the rotational analogue of mass. It's defined as I equals summation of mr squared with units kilogram meter squared. It helps us write rotational kinetic energy as half I omega squared. The radius of gyration, k, provides a compact way to represent distribution. We saw examples from rings, rods, cylinders, and spheres, and we noted that higher I means greater resistance to angular acceleration. From classroom problems to real-world machines like flywheels, the concept of moment of inertia is central to rotational dynamics. I hope this session gave you clarity on why the placement of mass matters so much in rotation. In our next discussion, we'll explore how to compute I for complex bodies using theorems of perpendicular and parallel axes. See you then.